I would like to thank Professor Svelto for inviting me to give a talk on probing cells and tissues by laser light for medical diagnostics. And I want to thank you, the young people who spent Friday nights sitting in a dark room instead of going outside into the sunshine. And I want to acknowledge the contributions of the group at the Department of Biomedical Optics in Berlin and the contributions of our medical partners at the Charité Hospital. To bring my talk into relation with medical imaging, I show you 3 objects of different size imaged by different techniques at different spatial resolution. Here you see a super resolution fluorescence image of a HeLa cell genetically engineered to express a photoswitchable fluorescent protein, and by looking at taking a wide field microscope and by looking at the fluctuation statistics of fluorescence, you detect signal molecules, and in this way you get a much better resolution compared to normal fluorescence microscopy. So the resolution is down below the diffraction limit, 120 nanometers, and this bar is 10 micrometers. This image is a bit larger, this object. It's the cross-section of the retina. You have a scan range of about 2 millimeters. The axial and lateral resolution are 10 to 20 micrometers. You see nicely different layers of the retina, and the OCT image nicely relates to the histological section. And OCT is, of course, an interferometric technique, and you use single backscattering. I'm not talking about OCT, and I'm not talking about superfluorescence microscopy. I'm talking about diffuse optical imaging on thick tissue, which means the imaging is based on multiple scattering and resolution extremely poor. Take a piece of tissue, let's say 6 centimeters thick. In the center, you have maybe a resolution of 1 centimeter. But what you see here, I give you an example. This is a fluorescence mammogram that's taken in vivo, and you see a fluorescent lesion, and since that lesion fluoresces, we know that its vasculature is leaky, it has holes, and then we know this must be a malignant lesion. It's not a benign, it must be a malignant lesion, and indeed it was. So in order to understand this, let me just go into a bit into basic physics. This is, we shine a laser light on a piece of tissue, and the laser light is absorbed, is scattered, and by absorption and scattering, you probe actually the pathology and pathopathology of the tissue. And in this talk, you will hear a lot of pathology, physiology. And in recent years, there have been several clinical trials on optical mammography, so there is a lot known on the optical properties of breast tissue, female breast tissue, and on breast tumors. And so I have chosen the breast as a piece of tissue, and we want to study that piece of tissue, and I will pose 2 questions. What can we learn about breast tumors by diffuse optical spectroscopy? The first question. And the second, what are the benefits for patients to be achieved? And at the end of my talk, I will give you parts to the answer. So we take a piece of tissue, and there are 3 material constants. One is the scattering coefficient, mu sub s, and the scattering coefficient in the near-infrared range is about 100 inverse centimeters. So 1 over the scattering coefficient is just the average distance between two scattering events. So this distance is 100 micrometers. until a photon travels through 6 centimeters of tissue, it's scattered many, many times. So we have multiple scattering. And because of the multiple scattering, you lose coherence and you lose polarization altogether. Now, transport of the radiation is governed by another quantity, by another material property, because you have to take into account the angular distribution. And because we have Mie scattering, the scattering is forward peaked. So we characterize transport of laser radiation by the reduced scattering coefficient, which is the scattering coefficient times 1 minus the average over cosine theta, where theta is just the scattering angle. And since it's forward peaked, this average taken over all scattering angles is very large. It's 0.9. So the transport scattering coefficient is down by a factor of 10 compared to the scattering coefficient, which means after 1 millimeter in tissue, you don't know anymore where the photon came from which direction. The third material constant is the absorption coefficient. And in order to penetrate, let's say, 6 centimeters of tissue, you need small absorption. So we are essentially restricted to the therapeutic window, extending from 600 nanometers to a micrometer or 1100 nanometers. And the absorption coefficient is, let's say, about 0.1 inverse centimeters. So the distance between two absorption events would be 10 centimeters. And this is a large cuvette. Actually, since the photons are scattered so many times, the trajectories followed by the individual photons is very long, much longer than the geometrical thickness of your tissue sample, maybe 8 to 10 times. So the photons have a lot of chance to get absorbed. Well, suppose you take an amplitude-modulated diode laser, not a picosecond laser, no, an amplitude-modulated diode laser. And this then either is remitted or transmitted through the tissue. And of course, at the output, the laser light is amplitude-modulated too. However, it's demodulated, the amplitude is smaller, and you have a phase shift. You have two quantities to measure, demodulation, phase shift, which means you can determine two unknowns. And these are just the absorption coefficient and the reduced scattering coefficient. If you took CW light, a CW laser, you could measure the reduced transmitted intensity. You would have one measurement for two unknowns, and you could not unravel absorption from scattering. Well, of course, this is the so-called frequency domain, and of course you can go to the time domain and take picosecond lasers. You could even take shorter lasers. When a picosecond laser pulse hits the tissue, then the photons follow many different trajectories of different lengths, so pulse broadening occurs, as was talked about by Professor Svelto. Now, we want to measure mu sub A and mu sub S prime, so we have to essentially set up the diffusion equation. Because of the many scattering events, you can model the radiation transport by photon diffusion. You set up the diffusion equation in time domain or in frequency domain. You solve it either analytically or numerically, and you take the solution, for example, the transmitted output power, that is the modulation amplitude, and the phase shift, and fit it to the experimental data to deduce the absorption and reduced scattering coefficient. Actually, it's an inverse problem. And even worse, it's an ill-posed inverse problem. So you have many, many artifacts or large changes in your distribution, in your spatial distribution, will give you only small changes on the outside. So I'm not going into any details, into the mathematics. Just keep in mind that all the data we derive from the measurements might have model errors, depending on the model you use to analyze your data. Suppose we have done the imaging or in time domain or frequency domain at many optical wavelengths. Then we measure the spectrum of the absorption coefficient. We deduce this from the data and of the scattering coefficient. And this spectrum can be just put into the contributions of the individual chromophores. And there are 5 major chromophores in the near infrared in tissue: oxyhemoglobin, deoxyhemoglobin, that's the red blood color, lipids, water, and proteins, collagen. And so the absorption coefficient is then given just by the molar concentration in tissue of these chromophores time the molar extinction coefficient, actually the spectrum of the molar coefficient. And this is well known. So essentially, when measuring the absorption coefficient over a wide spectral range, you can deduce the concentration of these chromophores in tissue, and you get information about physiology or pathophysiology. And the spectral dependence of the transport scattering coefficient is just modeled as an inverse power law. The scattering drops with increasing wavelengths. P is the so-called scattering power. It tells you something about the size distribution of the scatterers, of the maybe cellular components or the cells. And A, the scatter amplitude, about the scatter intensity. So here I show you the instrument built at the Politecnico. It was briefly mentioned in the talk by Professor Svelto. It's a time domain instrument because it uses picosecond diode lasers. It's wide spectral range because it uses 7 of them, spanning from 635 nanometers up to 1060 nanometers. And if you have many wavelengths, then you get robust for the concentration determination of the chromophores. And the output powers is not something like tera or pentawatts. Well, this is just milliwatts average power. The pulse repetition frequency, these are pulse trains, is maybe 20 megahertz. And the pulse width is fairly long compared to what we heard this afternoon. It's maybe 100 picosecond or 400 picosecond, depending on the particular laser diode. And then you feed all the laser pulses into a source fiber. You multiplex them in time. And the transmitted pulses, transmitted and broadened pulses, are collected by a bifurcated fiber bundle. And you count single photons in 2 detection channels, one for the visible photons and one for the near-infrared photons. And you repeat this experiment many, many times because of the pulse train. So you measure the pulse broadening or the distribution of times of light of photons, or if you want to call it, the time-dependent photon flux density. And then you can analyze this. Well, this was, here I show you an absorption spectrum, that is the spectrum of the absorption coefficient taken with this instrument. And you see here the filled symbols. These symbols were taken from the optical mammograms recorded. And the open symbols, they were recorded on the same patient or volunteer. And with a laboratory setup, wide spectral range time domain. And you see the data from this instrument nicely fit, is nicely interpolated by the laboratory data. Here you see there are 2 breasts, one fatty breast, one fibrous breast. And what you see here is the trailing edge of the absorption resonance of deoxyhemoglobin. That's the hemoglobin without the oxygen, without oxygen. And this resonance is due to oxyhemoglobin. The fatty breast has a lot of lipids in it, not too surprising. And you see collagen, and the fibrous breast it contains a lot of water. So the group here at the Politecnico has measured the composition of breasts of many breast cancer patients, and that is of the normal breast tissue. And they have correlated the concentrations with breast density. Now, breast density is usually inferred from X-ray mammogram. If you get an X-ray mammogram, you have 4 categories, and the highest category is the dense breast. And breast density is a risk factor for breast cancer. So you want to assess women according to this risk. But young women, you don't want to make an X-ray mammogram. You can do this for women older than 40 years of age. So by correlating the concentration of water and collagen with the breast density determined from X-ray mammography, and there's a strong correlation, you can essentially measure breast density by optical techniques, and this allows you to assess the risk for breast cancer in young women. Now, these are optical mammograms. They were shown by Professor Svelto, so I skip it and show you another instrument developed by another group at the University of Pennsylvania. And this instrument is designed to reconstruct the absorption and scattering coefficient, and therefore the chromophores, in 3D. And the patient lies prone and her breast immersed in a scattering liquid of similar scattering and absorption properties as the breast to relax the dynamic detection range. And the instrument uses 4 amplitude modulated lasers, that is, they work in frequency domain, and the remitted modulated light is analyzed for phase shifts and demodulation to determine the background optical properties of breast tissue. So up to now, you get the background optical properties, but no spatial distribution, no reconstruction. And in order to reconstruct, you take 6 CW lasers, and you measure the diffuse transmittance, imaging the transmitted intensities by CCD camera, lens coupled to the output plane, and you do not scanning like in the instrument here at the Politecnico, but you do fiber switching. We have a lot of source fibers. So what you do is you measure under many, many different viewing angles, and this allows you to reconstruct the optical properties, that is the concentration of the chromophores in 3D. And here I show you the results. This is the finite element model, the compressed breast. Here is the tumor. The tumor position and size were taken from MRI data, so as prior knowledge. And the planes here show you a cross-section of the mid-plane through the tumor, and what you plot is the spatial distribution of total hemoglobin concentration, of oxygenated hemoglobin concentration of deoxyhemoglobin, and of a so-called blood oxygen saturation. And what you can see right away, the total hemoglobin concentration and oxygenated hemoglobin concentration is high in the tumor, indicated by the black line, but there is no distinction of the tumor towards other disease-free parts of the breast for deoxyhemoglobin, and the same applies to the oxygen saturation. Here I show you just general results. Let's take a look at this line. The total hemoglobin concentration in tumors is on average larger than in normal breast tissue, and the same is true for oxyhemoglobin and for water. And for water, think of the dense breast. It had a higher water content, and it's smaller for the lipids, and the breast had a smaller lipid content. Scattering is always up, which means apparently because of proliferation, You have added scattering, a different size distribution, and the notable exception, and this I want to point out, is total blood oxygen saturation, which doesn't differ between tumors and normal breast tissue. And this is actually very surprising because tumors are known to be hypoxic. They lack oxygen. The tissue lacks oxygen. And so we have to, in order to understand this, we have to do some physiology. And I'm going to talk about regional blood volume, blood oxygen saturation, tissue hypoxia, tumor oxygen consumption, and small vessel volume fractions. It's like when you do atomic physics, you have to know something about atoms and quantum mechanics. If you do spectroscopy and tissue, you have to know something about the physiology of tissue. Here I show you the total hemoglobin concentration in the tumor versus that in the normal breast tissue and on a patient-by-patient basis. So for each patient investigated, the tumor always contained more oxyhemoglobin, and if you take total hemoglobin, and if you take the total hemoglobin concentration and you divide this by the concentration in blood, you just get the blood volume. That is the milliliters of blood per milliliter of tissue in the tumor. So basically, optics measures the regional blood volume. And the regional blood volume is a good discriminator for tumors versus normal breast tissue, but it won't be a good discriminator for benign versus malignant tumors. So let me remind you to the definition of blood oxygen saturation. It's just the ratio of the concentration of oxyhemoglobin to total hemoglobin in blood, and the same applies, of course, to tissue. You just change the reference volume. Now there is another measure of oxygenation, and this is outside the blood, in the tissue, and this is the partial oxygen pressure. And partial oxygen pressure essentially tells you how well you provide oxygen for basic metabolic processes. You can measure this partial oxygen pressure by a polarographic, that is an electrochemical method, and you need a Clark needle electrode, but this is an invasive measurement because you have to stick each time a needle into the tissue, and although it's being a gold standard, it's no longer applied. Here I show you the blood oxygen saturation in tumors and in normal breast tissue, again, on a patient-by-patient basis. So these are correlated blood. And these are data here from Milano, and these are data from, would you have maybe another pointer? Oh, okay. On the right, these are data from Berlin. And what you can see is the data scatter, and some of the tumor, and there are 48, that have an blood oxygenation saturation higher than that of normal breast tissue. And in the other tumors, there are 39, they have a saturation which is lower. So we divide the 87 tumors which we measured into two subpopulations. The subpopulation where the blood is better oxidized, is better saturated. These are the 48 tumors, and the other one where the blood saturation, the blood oxygen saturation is lower. Here I show you data taken from the literature, and this is partial oxygen pressure measured by the Clark electrode in normal breast tissue, and you see there is a broad distribution of pressures, and all the pressures above 10 millimeter mercury are called normoxia. This is a normal state, and well, you have a rather inhomogeneous distribution. But there are no measurements below 10 millimeter of mercury, so you have no oxygen, lack of oxygen or hypoxia. And if you take a breast tumor, the situation changes rather dramatically. You still have a broad distribution of normal oxygen distribution, normal oxia, but 30% of the measurements fall into the hypoxic region below the 10 millimeter mercury. So why is hypoxia so important? I want just to point out two facts. Hypoxic cells develop resistance to radiotherapy and chemotherapy, and this has, of course, consequences. And the second, a hypoxic microenvironment of cancer cells eventually selects for more aggressive daughter cells if there is proliferation, and enhancing the chance for metastasis. So essentially the tumor gets worse, or the malignancy of the tumor gets worse. Tissue hypoxia is, of course, an imbalance between oxygen delivery and oxygen consumption, and I'm not going into the oxygen consumption, but it's focus on oxygen delivery, that is on regional blood flow, blood oxygen saturation, and the structure of the small vessel bed where the oxygen exchanges or diffuses from the blood, from the red blood cells into the tissue. So we need a tissue model, and the simplest tissue model is that of Koch, just for the so-called capillary bed. The tissue consists of parallel, identical capillaries, being all parallel. It's a crude model, I suppose. And each capillary is surrounded by a sheath of tissue which uses up the oxygen it metabolizes. Of course, all the cylindrical sheaths are identical, and at the arterial end, you have an oxygen saturation of StO2 arterial, and this oxygen saturation then drops towards the venous end, and this drop is actually linear. It's given by the metabolic rate of oxygen inside these tissue cylinders, and the metabolic rate of tissue consumption is given in milliliters of oxygen per milliliters of tissue per minute. And you multiply this just with volume of the tissue cylinder, and you relate this to the rate of oxygen delivery. And V blood is the velocity of the blood in the capillary. So here you have blood flux, and this is the oxygen concentration in the arterial blood. Now, we could determine the metabolic rate of oxygen in the tumors, for example, if we knew the blood flow, but we have unfortunately not measured blood flow. So we relate the blood flow by the blood volume. Blood flow is given in milliliter blood per milliliter tissue a minute by the blood volume, which we measure by the total hemoglobin concentration in tissue, and the mean transit time the blood takes to perfuse through the tissue. We don't know the mean transit time either, but what we can do is we can essentially determine the oxygen consumption in the tissue during that mean time during the mean transit time that's given just by the metabolic rate of oxygen times the mean transit rate. And then we can express that oxygen consumption as the oxygen extraction fraction. And this is nothing but the drop of the oxygen from the arterial end to the venous end, normalized to the saturation at the arterial end, and times epsilon, and epsilon is known, that's the so-called Hüfner factor. It's the oxygen carrying capacity given in milliliters oxygen per micromole of hemoglobin, and then you have here the total hemoglobin concentration which you measure and the arterial saturation. So basically we can measure oxygen consumption during a mean transit time. Well, if we want to do that, then we have to measure the oxygen saturation in the feeding artery of the tissue. We haven't done this, and we can set it equal to 1. That's a very good approximation. Oxygen saturations are about 97%. And we need to know the oxygen saturation in the draining mean, which we haven't done either. So we cannot really measure the true oxygen consumption, but we measure an apparent oxygen consumption because we measure the blood oxygen saturation in the tissue, and the tissue consists of small arteries, arterioles, small capillaries, and small veins, venules, each with its own oxygen saturation, and what I've given here are the relative volume fractions. So the oxygen saturation in tissue is given as a volume-weighted average over the saturations of the three small vessels. And there are reports in the literature that the fraction of the small veins are considerably larger in volume compared to the arteries and the capillaries. So what we do is we just divide the tissue in the arterial part and the venous part, and what we can then do is we can relate the apparent oxygen consumption to the true oxygen consumption just by this fractional volume of the veins. So what we measure, the apparent oxygen consumption, is always a lower bound, and the same applies for the apparent oxygen extraction fraction and the true oxygen extraction fraction. Now let me show you the total hemoglobin concentration of the poor 87 patients, and we have arranged these measurements just in ascending order. And now I'll show you the corresponding oxygen extraction fraction corresponding to this ordering, and you see the oxygen extraction, it falls down, and when you multiply the two, then you get the apparent oxygen consumption, and this apparent oxygen consumption is basically flat. So we know we measure essentially a constant oxygen consumption during the mean transit time of blood, and the same, of course, you obtain if you do not plot it versus increasing blood total hemoglobin concentration, but versus the hemoglobin concentration itself. So let me summarize on the tissue optical spectroscopy. On normal breast tissue, we measure a volume-weighted average of blood oxygenation over arterial, capillary, and venous blood. We measure an apparent oxygen extraction fraction related to the true one by this volume fraction. The same applies to the tissue oxygen consumption during blood mean transit time, and we know that this oxygen consumption is about constant over the entire cohort of patients. Now, let's take an experiment from PET, positron emission tomography. And positron emission tomography has measured the blood flow in the normal breast of breast tumors. And this is a narrow distribution and is 0.06 milliliter blood per milliliter of tissue and minute. And when we use this, then we can essentially calculate the mean transit time to be about 8 seconds. And when we take this number and the oxygen consumption, the apparent, which we measure, then we get an apparent metabolic rate of oxygen of 3.2 microliters of oxygen per milliliter of tissue admitted. And this is a result very close to a result measured by PET many, many years ago. So the interpretation seems to be okay. Now let's go to tumors. And here I show you the vasculature of different tissues, of the colon, of skin, and of muscle. And down here, the vasculature of corresponding tumors. And what you see is there is additional vasculature, there is additional blood volume, which we know, but the structure of the vessel bed is totally different. The structure has nothing to do with the structure in the host tissue. And not only structurally, the vasculature in tumors is functionally abnormal because you have shunts between arterioles and venules. You have collapsed vessels, so there is no blood flow anymore, or the red blood cells cannot pass. You do not control the spacings between the veins, the small capillaries, which is very important, and you do have openings where cells and proteins leak out. I skip this. And here I show you the apparent oxygen consumption of breast tumors in the two subpopulations which we defined. Those with a blood oxygen saturation smaller than normal breast tissue, and what you see is you get essentially a straight line. That's essentially blood oxygen consumption over blood volume, and the data scatter around a straight line, and the straight line is just the apparent oxygen extraction fraction, and this is 38% in this case. The same, of course, applies to the other subpopulation where the blood oxygen saturation is larger in the tumor than in normal breast tissue. Here, because the saturation is high, the extraction is low, and the extraction is only 20%. So let me summarize. Let me summarize. We measure an apparent oxygen extraction independent of blood volume, and the apparent oxygen consumption during mean transit time is proportional to blood volume, and this means that you cannot saturate the capacity of breast tumors to utilize oxygen. They take the oxygen they can get. Here I show you here I give you the summary of our measurements on total hemoglobin concentration, blood volume, apparent oxygen extraction, and oxygen consumption. Let's go to the blood volume. You see I don't have another pointer. No, I don't have another pointer. Okay, I'm sorry. So the blood volume in the tumors is always larger. These two columns, they are just proportional to each other. The oxygen extraction fraction, it's smaller for the subpopulation where the saturation is larger than in normal breast tissue, and it's smaller than normal breast tissue. It's larger than normal breast tissue when the oxygen saturation is smaller than normal tissue. And when you multiply essentially these two columns, you get the apparent oxygen consumption. And what you see here, breast tumors always consume more oxygen than normal breast tissue. This is twice or three times as much. And this means that the so-called aerobic glycolysis, that's the Warburg effect, where you use a lot of glucose to produce energy, cannot be made solely responsible for the reduced oxygen extraction fraction. The oxygen extraction fractions, there are lower estimates, of course, and the differences in these oxygen extraction fractions might be due to the differences in this volume fraction of the small veins. Oh, thank you so much. Thank you so much. Oh, okay. Now let me return to this figure. We have the two subpopulations, the tumors with a higher, 3 minutes. Okay, the subpopulation with a higher saturation and the subpopulation with the lower saturation. So we can essentially classify those two subpopulations as the red ones, high perfusion, low extraction, low consumption. The blue ones, low perfusion, high extraction, high consumption. So you ask me what will be the more what will be the more problematic, or the tumor with the tumors with a higher malignancy. And if a tumor consumes more oxygen, if it's less perfused, if it has a higher oxygen extraction, I would guess it's the more malignant tumor. And actually, there is a clinical trial which supports this view. A group in the United States has carried out a small clinical trial involving 41 breast cancer patients, 42 breast cancers, and the breast cancers were so large you couldn't operate them. And these patients underwent chemotherapy to shrink the tumors before or prior to surgery. And after surgery, the excised material was looked by pathology for residual disease. And the residual disease, if there was no residual disease, then they are called the complete pathological responders, and there were just 12 of them, and they have the good prognosis. And there were 30 tumors that were non-pathological responders. And the group had measured optical spectroscopy prior to chemotherapy, and there were no differences between the two groups apart from blood oxygen saturation. The normal breast tissue didn't differ, but the tumors differed. The non-pathological complete responders had on average smaller blood oxygen saturation that is corresponded to our blue group. So let me summarize. I have, unfortunately, to switch this. So I want to answer the question. Well, what can we learn about breast tumors by diffuse optical spectroscopy? We measure composition of the chromophores of normal breast tissue. And breast tumors find, for example, that breast tumors have a lot of water. We measure regional blood volume and find that this can very well discriminate between tumors and normal breast tissue. We get information about tissue structure by measuring, that is, cellular density and cellular size from scatter amplitude and scatter power. We measure the apparent oxygen consumption from blood oxygen saturation, normal tissue and breast tumors, and may even take advantage of that. And something which I did not go into though, we measure the vascular leakiness of carcinomas using macromolecular contrast agents. So, and what are the benefits for the patients? From breast tissue composition, you can make the risk assessment of breast cancer. From vascular leakiness, you differentiate between benign and malignant lesions in analytical mammography. And from blood oxygen saturation, you get at least a response prediction to neoadjuvant chemotherapy, or maybe even a handle on malignancy. And of course, one can use other chromophores to monitor the response during that chemotherapy. So let me conclude and say tissue optical spectroscopy and diffuse optical imaging using laser radiation are still at their infancy, and future applications and benefits will be expected. Thank you very much.